Okay, so and this is my first experience here, which has been a wonderful one so far. I had a wonderful opportunity to visit Children's Hospital of LA, then came up here, and so it's been a really nice West Coast tour. I honestly didn't know much about CFRI until the last couple of years, and Siri started working on me. And the opportunity to be here has really been wonderful. What a great community! What a great mix of healthcare providers and care providers together. So you guys have a really nice bridge. We have another bridge. If you take a look there, anybody, does that look familiar to any? Does it look like any other bridge you've ever seen before? Maybe just sort of, kind of. Maybe. All right. Well, that is the Roebling Bridge, which was built by. I always say J.K. Roebling, that's not right, by J.K. Rowling, but anyway, Roebling built that as a warm-up for the Brooklyn Bridge, and so it is over the lovely Ohio River, which is best seen at night, if you know what I mean. It's kind of brown otherwise. But otherwise, what I was going to be talking to you today is about building the bridge to a cure, which has been really been what I feel very honored and lucky to be part of over the last 25 years. Everybody seems to give their brief testimonial about how they got into CF. I honestly didn't know anything about CF until I was a third-year medical student. And I grew up in Iowa, and I didn't know what to do for my, excuse me, before I make a mess or ruin the computer here. I didn't know what I was going to do. I was sort of finished with third year. I was going to be internal medicine, pediatrics, or OBGYN. I was like, And so I had a friend who was getting his MD, PhD, working in a lab focused on cystic fibrosis, and I said, sounds good. And so I was able to get a 1 year, $1,000 a year, which was big money back in 1989. But anyway, it was, happened to be, we were sort of in a race with other labs to figure out, it's this chloride channel, it's that chloride channel. And then sort of at the end of the year, there was this thing called the CFTR gene that was identified. And it was sort of like the whole world flipped in one day. And that kind of lit my passion. So I came at it first from a science side. And then I became a pediatric pulmonologist, and then I got to know the personal side. And I also provide care to CF patients. I have about 50 or so that I take care of, and it's been a great honor and the best part of my life. So briefly, I'm just going to have 3 parts to my talk. Some of it's going to be background, I understand, but I think it's a helpful foundation to make sure we're all on the same page. A little bit about understanding the role of CFTR and CF, and also acknowledging it really has gained a lot of interest in the healthcare community and the research community as really a leading a disorder in which new techniques and new understandings of the gene are really translating into new therapies. And that's really culminated in the last few years with CFTR being really determined to be a really appropriate and meaningful target to change the disease. In other words, making CFTR better actually works. Sounds like it makes sense, but now we actually have data that says it does. And then finally, roughly the last half, I'll talk about new developments, things that are in the pipeline that have to do with CFTR therapies and not, because CFTR therapies is not everything, and clearly there's a great need outside of that. And how we're moving towards the concept of clinical trials in a test tube. And I think that's a really exciting direction that will be coming. It is coming and becoming quickly. So does anybody watch America's Got Talent remember the Christensen sisters? They were a couple of participants a couple years ago who were sisters with cystic fibrosis. They made a good run, but they didn't, quite. I don't think they got past what's his name? Simon. Yeah, Simon. Simon shut them down, I think, if I'm not mistaken. And then on a very heartfelt moment, Sarah Murnaghan, who was a 10-year-old patient at Children's Hospital of Philadelphia who was awaiting a lung transplant. Her story really changed the way we look at lung allocation, acknowledging that some people were being left out in transplant listing. And so those were just a couple of examples of very sort of personal stories that sort of captured and highlighted CF in a personal note. In 2015, our former President Barack Obama really called CF out at the State of the Union address, and really noting noting that really the onset or the concept of precision or personalized medicine, sometimes used in, synonymously, but really the idea that we should make therapies specific for each patient and their form of disease. And in the bottom quote, in some patients with cystic fibrosis, this approach has reversed a disease once thought unstoppable. And even since that time, there's been dramatic changes in what we can offer to CF patients, and just reminding us that how rapidly this field is moving forward and changing. So just to briefly give a one-page reminder of what CF is, it's a disorder in which a gene doesn't work. That gene's name is there. We call it CFTR. You can call it by its longer name, cystic fibrosis transmembrane conductance regulator. I'm done. That's the last time I'll say that. When it doesn't work correctly, the symptoms of CF occur. The genetics, about 1 in 3,000 births in the US. It varies quite a bit depending on ethnicity. California is quite unique with a heavy or a large Hispanic population, which has very different groupings of mutations. It's a roughly 33,000 patients in the US, roughly 70,000 worldwide. Those are certainly estimates. There's lots of countries where it's probably not even reported. And so we're still learning more and more about that. Where I work now, we interact a fair amount with communities from the Middle East, and coming to appreciate it's actually much more common there than I had appreciated. And I think that we're learning more and more about new communities over time. It's called an autosomal recessive disorder, meaning you have to have 2 copies of the gene that don't work correctly to have the symptoms, while carriers who just carry one don't have symptoms typically, but can carry a risk of having children with CF. It can affect a number of organs, as noted here, and lungs are frequently involved, but it doesn't mean other symptoms don't occur. GI symptom can also be really quite profound, including the liver. Roughly 2,000 ways the gene can be broken. But we're learning a lot about that and how to really come up with therapies that go after those different ways that the gene doesn't work. The median predicted survival is about 41 years. I think that's a great accomplishment, but that's only halfway there. And so I think we all acknowledge we have plenty of work to go. But over 50% of patients with CF are now adults, and I think all of us see that as a huge milestone that has really just occurred over the last 2 to 3 years, and we look forward to keeping going forward. So EBM, that stands for evidence-based success, or evidence-based medicine, using traditional approaches of clinical trials, randomized double-blind placebo-controlled studies of new therapies, working with the FDA, sometimes not actually with the FDA. We've seen a very steady improvement in outcomes for CF patient here. We're looking at median survival over the years, and these are all therapies that are commonly used in cystic fibrosis, which have been associated with that. PERT is basically enzymes. I mean, you had to make them short and sweet, so I apologize for all the abbreviations. Dornase alpha, ibuprofen, azithromycin, a variety of inhaled antibiotics, hypertonic saline, and most recently the advent of CFTR-directed therapies. And we're obviously really excited by these changes. But there is a cost, and I think we heard about it in great detail from Dr. Reichert last night, how these great advances in our available therapies become a challenge. The time spent doing therapies for patients with adults with CF is estimated around 2 hours, and that's on an average, maintenance day. And as you can see here on the left is sort of an example of things that we may ask of patients to do, and the right is what they want to do, perhaps, and you can see that things are getting crunched. And I think what we're considering as we go forward is how can we make what's available on the left more appropriate for, so that on the right side, that becomes the bigger part of the pie. When CF doesn't work, it causes disease in a variety of different organs. And we think of it a little bit in terms of upstream and downstream contributors. Upstream means basically at the very root of the problem, where CFTR is doing the kind of the fundamental thing. It definitely moves chloride, which is again a salt, and it also regulates sodium, the other half of chloride, sodium chloride, and those are really important in hydrating the mucus. And when it doesn't work correctly, that mucus is thick and sticky and it's hard to clear. In addition to that, we've come to more recently appreciate that bicarbonate is a really critical player in CF, and it's believed that the lack of bicarbonate, which is that HCO3, when that's not moved correctly, that also contributes to mucus that's really thick and sticky. And we're coming to appreciate that these are all likely players. When mucus doesn't work correctly, there's either too much, or its content is incorrect, or its properties are not quite the way it should be. over time, that sets up a kind of a perfect storm, if you will, of infection, inflammation, which ultimately leads to airway damage. And the picture on the top, I guess it'd be your left, is that's just from a lung transplant patient looking at the lung of the patient. What we see, that really purpley area, can I actually? Yeah, I can do that. See, up here, this is actually an airway tube, a bronchus, and this is a wall that's kind of thickened, and in here is just a bunch of white blood cells and mucus. And so it's just showing us a big plug of infection and inflammation going on. And down here, unfortunately, is the example of the lung, which is really damaged. And these large areas that are kind of like big, almost like holes, are big dilated airway tubes that don't work correctly anymore. And unfortunately, they are full of mucus and infection, which creates all the symptoms that we all know about in cystic fibrosis, end-stage lung disease. So when we look at the lungs in more, or the airways in more detail, on the left side is an example of normal airway, and we have this cell down here. Whoops, can you, my little guy? Nope, he doesn't show up. So anyway, on the bottom is the airway cell. Those little things standing up are called cilia. They are basically microscopic conveyor belt, and they help sort of move mucus all day long. And above it, it's a nice normal layer of mucus which catches things normally and clears them out before we really even notice them. On the right side is the example in CF where that mucus layer is a lot thicker. It's full of a variety of different things that actually make that mucus hard to clear. It has too much DNA in it from cells that have come in and die, and DNA, if anybody's worked in a lab, is very sticky. It tends to pull water into it and therefore kind of push down and smush the cilia so they don't work very well. And there's recent evidence too that mucus release is not normal. It gets stuck basically on the release and it holds it in place, and that sort of probably contributes to some of the infection risk they have. And finally, at the very bottom is the problem with the CFTR actually in the cells not moving the salts and water the way it's supposed to. And so when we look at CFTR, going from the gene to the symptoms, we start with a loss of CFTR, which then over time can create kind of a cycle of mucus accumulation, infection, inflammation, and ultimately airway damage. And what we're looking at on the top side over here, these are just airways from a patient who's undergone a CT scan. And these kind of large dilated airways are the abnormalities where most of the problems arise. Whoops. But the exciting thing is we have a lot of therapies that can target CF. And when we look at things that are treating the symptoms, it includes medicines like hydrators and mucolytics, that would be hypertonic saline and Dornase alpha, antimicrobials, a variety of different antibiotics, anti-inflammatories such as azithromycin, and, well, Luke, are we going to debate, is azithromycin an anti-inflammatory or an anti-infective? You're not going to go there, all right. So he'll go with me, but point is, yes, we realize this, there's a lot of action in this area too. And then most recently, though, over the last few years, has been the advent and sort of the introduction of modulators, which help CFTR work better. And our future, gene transfer, gene and RNA editing, and use of patient model systems to help predict best therapies for patients. And we'll talk more about that later on. So what does CFTR look like? We actually kind of know. This has been one of those holy grails in CF for a number of years, trying to get a good picture of CFTR. And the reason that's hard is CFTR is normally a protein that sits in a cell membrane. And what that makes it, it's just really hard to get it in the right configuration to know what it looks like. But recently, groups has actually identified what CFTR looks like with the best resolution we've ever seen before. And this is from their work that really just came out this year in 2017. And what we're looking at here is a protein that is part of a big family. The family, they're called traffic ATPases. There's at least 70 of them. There's probably more now. They do a lot of things they do a lot of normal things that help keep us healthy. And there are certainly disorders where members of this family don't work correctly. One example is chemotherapy resistance. Drugs that are used to treat cancers called chemotherapy agents are very good at killing cancer cells, but sometimes cancer cells react to that by turning on genes which pump out that chemotherapy so it no longer is effective. And one of those types of proteins is actually a member of this family. So there's a lot of interest in understanding this class of proteins. It has these two parts that sit in the cell membrane up here, these kind of long, relatively skinny part, and those are called transmembrane domains, or TMDs, and they basically hold CFTR in the cell membrane. And then down below are these parts which kind of bind and power the protein to open correctly. These are called nucleotide binding domains, or NBDs. And the one thing that's kind of, for those of us in the field who are really, really nerds, is this kind of red strip. It's called the R domain, and that's important in regulating also how the protein opens. Nobody really knew where it was and what it did until this came out, and so it really gives us a much clearer insight in how this protein works. And with that type of information, we can start to think about really making drugs that are, or approaches that are really targeted at specific causes of CFTR problems. So how do you get from a gene to a protein? This is a cartoon that came from an article over 10 years ago, but I think it gives probably a pretty good look at that. Down here is where the genes live. They live in the nucleus, and they are first, I can see it on mine, and there we go. You can't see, there it is. Nope, you can't see that. Okay, down below is the gene is stored in the nucleus, and it is its first step is to be a template is made that's called mRNA, and that's called transcription. And after that, it gets converted into a protein, and that's called translation. Then that protein has to go through a number of steps where it gets right, where it gets in the right shape, it gets all the right sort of whistles and bells so it can do its job. And then it finally goes up to the cell membrane for in the context of CFTR, where it goes and does its job, helping regulate sodium and chloride and bicarbonate and water transport. And the reason I bring this up is the mutations can happen anywhere along that way. And a problem that is down at the bottom in the transcription area is not going to be the same approach if the problem is way up at the cell surface, where CFTR maybe is made, but it just doesn't work correctly once it gets there. So that's the kind of concept behind really developing CFTR modulators. We actually target the various problem that is unique to each of the different kind of CF-causing mutations. If you look at CFTR, there's really only three parts that make it do its job, and three things that you can fix or improve to help restore its function. And that really boils down to the number of channels that sit in the cell membrane, how much time the channel is open or closed. Oh, thank you, there's a pointer. Whoa, and I almost lost my water. Sorry about that. We may have a very short talk today. Here we go. Yeah, nope, that's the advance button, by the way. Sorry about that. And I am on fire today. Yes. Okay, well, we're back. I'm going to put this back down, if you don't mind, before I cause more trouble. But there's three factors that we can influence to make CFTR work better: the number of channels, how much time it spends open, or how big the channel is. And that's really it. I mean, I know it's a complicated field, but if it really boils down to those three places that we can make a difference. And so far, modulators help with N. They help get more channels in the membrane, and they also help with the PO, which is open channel probability, or how well the channel is open. We do not know how to make a bigger channel yet, but who knows, maybe down the road. So these are all the types of modulators that we can have, and I know that's kind of a small picture, so it's hard to see them, but the point is there's a lot of them, a lot of ways that people are thinking about this. There's potentiators, that's what ivacaftor is. There's correctors, that's what lumacaftor is, and more recently tezacaftor. There's suppressors, that's what atalorin was trying to be. There are stabilizers, that's the type, the drug that was being made by Novartis. It's a hard one to say, cabinafsenat, anyway. It had too many O's for me to remember. An amplifier, this is one that's being developed by a company called proteostasis, which basically increases the amount of RNA. And then most recently, using oligonucleotides to potentially try to target the RNA that is one of the steps in making a protein. And so these are all kind of coming on the horizon, and they're sort of in different stages of development, and some of them have obviously made their way from the laboratory and into the clinic. So how have we made, yes, my cilia are waving, I'm so happy. So I was worried about that. So how have we gotten these drugs to patients? Well, a really important and valuable way that has been really unique is the use of airway cells that came from patients who underwent transplant. And the ability and the willingness of patients to donate tissue to do this has been instrumental in helping us be able to bring these drugs to patients. We meaning the scientific community, has gotten pretty good at growing these cells. And what I'm showing you in this picture is just an example of cells from the side where we can see CFTR in green. And then down below are some other markers that are telling us that these airway cells are basically oriented the right way and doing their job. And what the slide on this side, if I can make him run again. Here, we'll see if he'll do it again. There we go. Those are cilia that are moving when we look at down on the airway cells. And these are all critical for helping us be able to bring modulators to patients. It's unique. Most drugs that go to that make it to patients go through animal models to really show that they're effective. There's the animal models available for CF are not very practical for doing studies of CFTR modulators, and therefore we've had to rely on these airway celled cultures. And the good news is they've been really good, and they've been quite good to this point to advance the field. So I'm going to briefly talk about the G551D CFTR, and I think this all began or became important in the mid, I guess 2010 roughly is when the results of these studies began to come out. But I show it mainly as just it's an example of how you can go from a molecule to patients through this pathway. It's the third most common causing CF mutation, found in roughly 4.5% to 5% of the CF population, has a higher incidence in Ireland. The channel doesn't open correctly. That's its big problem. It can get to the cell membrane, but it just won't work. And so the strategy is to try to make it open. And the development, again, happened in airway epithelial cells. And what we're looking at here is an example of results from one of those airway epithelial studies. What we're looking at is the transport of chloride across a layer of cells. And they call that short circuit currents, which I won't get into the details why, but I'll just call it CFTR activity. And it's kind of looking at the electrical properties. And as we look on the x-axis, it's just time, and the y-axis is essentially CFTR activity. And that first little arrow down at the bottom is where we try to activate CFTR the normal way, a way that raises cyclic AMP, and that should activate CFTR, but it doesn't. You can see not much happens. And then up above, you'll see where increasing doses of the X770 have been added, and you can kind of see this stepwise increase in the CFTR activity. And that's just one of those ways that we show that the example of how we can test these drugs and determine that they truly work in airway cells derived from patients with CF. At the very end is a blocker we add, which should close the channel and therefore drop the CFTR activity, and it makes us feel confident, yep, this is actually CFTR. And next thing that was determined with the X770 after it became known as ivacaftor, it does other things beyond just move the chloride. It actually helps restore the sort of downstream consequences of moving chloride and bicarbonate and water correctly. And what we're looking at in the top picture is the amount of fluid on top of those cells, and that's called the ASL, which stands for airway surface liquid. And normally, normally if you don't have CF, you have a nice even layer. You can see it sort of the top number where it says wild type or WT CFTR, and that's kind of what it ought to be like. Down below is the example of G551D cells, in which it goes down to a much lower layer after you add a common volume. And then, I think I'm going to try one more time. Nope, in the middle, yep, there we go. In the middle is the, I have an arrow which says 770. They basically have added the drug to the G551D cells and brought up the volume. So it's telling us not only are we moving ions correctly, we're actually restoring fluid movement. And down below is even a step further, where we've restored the movement of cilia. And that's really what that fluid needs to do, is allow the cilia to do its job. And so as we move from left to right, we're looking at the ciliary beat frequency, or CBF, how rapidly the cilia can move. On the left side is the G551D cells that are stimulated in sort of the normal, natural way. And then there's the addition of 770, and you see that there's an increase where it actually gets up to be the same as what we see in the normal cells. And so, again, these types of tests in airway cells were able to help us feel confident that these drugs are actually doing what they're supposed to. And this culminated in the study that was published in 2011 of ivacaftor in patients with one copy of the G551D mutation. This study included 161 patients over the age of 12. They had lung function that was kind of in the moderate lung disease stage. We're going to try another one? Oh, thank you, Luke. Luke has saved me. So before I completely missed, you just can't see it very good over there. It does work, see, over there? And then I go there. Oh, there it is. All right. So this is looking at lung function. And patients who were put on drug, this rapid sustained increase in lung function of 10% that was present for the whole period of treatment. And down here is looking at the rapid reduction in sweat chloride below the diagnostic level, in the treated group, which is shown, this is the placebo, and this is the diagnostic cutoff of 60 millimolar, and down here is the actual average range for the patients on drug. So really a dramatic effect, and a number of other outcome measures were seen that were benefiting. But it really changed the field. It all of a sudden set a new benchmark that we could get to. Is it the final benchmark? Probably not, but it's certainly a really powerful place to get, for us to aim for additional therapies. So how about F508? Most common cause of CVF, the F508del. It's basically a mutation where there's a missing amino acid called phenylalanine in one spot at position 508. And what we're looking at here are cells from patient who does not have CF, and normally the CFTR is right here at the top of the cell in green. And down over here is the cells derived from a patient with 2 copies of the F508, and we see there's very little up here where it belongs, and most of it's kind of scattered throughout the cell, and it's in some of those compartments where it just can't get to where it needs to go, and it's being broken down. What's wrong with CFTR when delta F508 or when F508 is removed? This is sort of another cartoon picture of CFTR that we've used in the past. These are those transmembrane domains. These are the nucleotide binding domains. And here's where F508 is. It's kind of on the outside surface of this part of the protein. It's called NBD1. And when it's missing, that domain doesn't fold up very tight. It's kind of loosey-goosey, and it's also normally supposed to interact with another part of the protein, and it doesn't. It doesn't do that very well. And when those two steps happen, it's unable to really get past the next checkpoint, and the cell says, "You're not right," and they go and break it down. And the problem, what this also highlights is that delta F508 is not a single problem. And while it is one missing amino acid, that causes at least 2 and maybe even more downstream problems. And that also tells us why we need additional drugs to help delta F508 work, because a drug may only help one of those problems, but it maybe doesn't help all of them. And that's kind of the concept behind the development of new therapies for the target F508. So to help delta F508 work better, using the same kind of concept model system that was used before from patients who'd undergone transplant with 2 copies of F508. The drug VX809, or I guess the compound VX809, was eventually developed into the drug Lumacaftor. And what we're looking at is increased activity of CFTR with increasing concentrations of VX809. And these are log scale, but you see this kind of uptick, and then we kind of hit a wall. We can only get so much improvement, but with that drug alone. However, if we add 770, which is ivacaftor, on top of that, all of a sudden you double that effect. And what you've done is, on step 1, you've helped it fold a bit better, and in step 2, we think we've made it open a bit better. And those 2 things are really the concept behind Orkambi, which eventually became approved just a couple years ago. So the traffic and transport studies were huge, 1,100 patients with 2 copies of F508. You see this word RDBPC, that's randomized double-blind placebo-controlled trial. That's one of those big regulatory things you need to see often from the FDA, for the FDA to sort of feel confident about a drug being active. And I looked at 2 doses of Lumacaftor, which is the folding drug, and plus ivacaftor, the opening drug. And what we saw was, indeed, both doses had a significant improvement in lung function. And this is the placebo group down here. These are the 2 doses. And we also had a reduced risk of pulmonary exacerbations. These are the 2 dose groups, and this is sort of when they have an exacerbation compared to the placebo group, who had them more rapidly. It's basically your risk of remaining without one is what it's measuring. And that was great, no question. And eventually this was approved in the US. There was regulatory improvement in other countries, but it's been slow for some of the national health systems to adopt it, and that's primarily because of cost. The other point is it's definitely moved the needle, but it's a long way below what ivacaftor can do. This is looking at the Orkambi effect originally in the delta F508 homozygotes, around 3% improvement in lung function, and this is the effect of ivacaftor in patients with G551D. So that raises the question, how do we get up there? That's what we really want to do, and that's our goal. And so the next bit of work that has been coming along and actually just was released in the last 2 weeks is work with with what are called next generation correctors. And you'll see NG, that's kind of that's, if you want to be cool, you call them, next gen, that's the cool word. So anyway, but how do we boost this effect? In other words, we've seen that kind of ceiling that you can get to with IVA and Luma, which is Orkambi. How do we get above that? And so for that, we add a second corrector called a next gen, which helps another one of those steps in the folding pathway. And that's why these drugs kind of are all of a sudden combined together. Corrector A, like Luma, here we go, will help step 1 in folding. Corrector B helps step 2 in folding. And potentiator helps that delta F that got up to the cell membrane open better. And this is really where at least the next step is going. And so this study, there were results, and I'll show you just an example, but just showing the amount of effect that can be seen with these next-gen drugs above a background of therapy that's very similar to Orkambi. What we're looking at here are 3 different drugs that are called next-gen. There's VX440, there's VX152, and VX659. And I'm just showing, ultimately just going to show data on the first one, which has the most. These are small studies. These are like 26 subjects here. This is 47 subjects here. These are 14 subjects. So these are small numbers, I think. I just want to make that point. That being said, the effects were clearly evidence and makes us very enthusiastic about the potential for these approaches to become new therapies. What we're looking at is the change in lung function and the change in sweat chloride after treatment for 28 days in delta F homozygotes and also delta F508s with only 1 copy of F508, and the second mutation doesn't work, and that's called an FMIN, which another cool word that you can start using. But what was found was there was this improvement of about 10% in the FF508, and they were already being treated with a drug very similar to Orkambi, so this is kind of on top of the Orkambi effect, if that makes sense. But what was amazing was the people who only had 1 copy had this huge jump of 12%, and that's just staggering. I don't think anybody quite expected that. And the changes in sweat chloride were around 30 points here, and some of the later studies have even shown perhaps higher levels. And so really showing that we're starting to move the needle in this population of patients who only have 1 copy of F508, which is really exciting. And I will just show you brief results from one of those studies. One of those is, again, the VX440. That was the one that is getting closer to getting into phase 3. And I'm first going to show you some of the results of the patients who have 1 copy of F508, and the second mutation is not predicted to have much activity. So what we're trying to really do is just make this guy work. And we only got 1 to work with. And so they looked at 2 different doses of the active drug, or the new drug, the next gen of 440, combined with tezacaftor and ivacaftor, which is, it's kind of like a next iteration of Orkambi, if that makes sense, compared with placebo. And these are small numbers, 18, 18, and 11. So these are, again, I just, acknowledge it's not a lot. But what we're seeing here is the change in lung function of the 2 dose groups. This is the lower, this is the higher, and again, it happens within 15 days, and it's certainly perhaps even on the upswing when you get out to 28 days. And this is the placebo, who really didn't show us much change at all. So pretty profound effects. And hand in hand with that is looking at the sweat chloride changes, which is here. The placebo group is here, not a whole lot of change. This is the low dose, and this is the other dose, the second dose, the higher dose. I guess it does raise the question, are we at the highest dose? Could we do better? Because it doesn't look like we've maxed out yet. So those are certainly possibilities as we get to bring these drugs forward. But I think there should be a lot of enthusiasm that this approach really actually could work, where we could add a second corrector on top of what we currently do and really extend the availability of therapies to patients who have 1 or 2 copies of F508. So I think I would like to say, just to cover the just sort of first part, the small molecules are really changing the face of CF. For patients who have 2 copies of F508, which is roughly half of the CF population, lumacaftor and ivacaftor is currently available. Tezacaftor and ivacaftor is finished in phase 3 studies, which also shows clinical benefit, and the newest next generation edition has really even improved upon those. It's opened the door for this group of patients who have 1 copy of F508, particularly with the tezacaftor, ivacaftor, and next gens. We already have ivacaftor available for patients with gating mutations, partial function, and R117H, which is somewhere around 6 to 7%. And there is a really critical group here who need our consideration, and this is the patients who don't have one of these different types of mutations. And we'll certainly spend some time talking about how we're thinking about ensuring they get CFTR-focused therapies. So I'm going to take us through some of the CF pipeline. And there are a lot of ways that people are tackling CF therapies, both starting with CFTR and also going down to a variety of the downstream manifestations. And I'm going to highlight just 3 of those areas, talk a little bit about some additional approaches to make CFTR work better. I'm going to talk a little bit about recent results from an anti-inflammatory study, and then also some CF Foundation observational studies that I think will be of relevance and interest to people. These other ones I will certainly mention, but they don't have a lot of new data that I was going to present that I thought was quite ready for sharing, but at least let you know there's a lot of activity going on. So when we look at CFTR strategies that are going on in clinical trials, there are a number of potentiators, 2 that are listed here. Interestingly enough, this one is essentially a once-a-day form of ivacaftor, and most people think that's pretty exciting because how many people have to take medicine more than once a day? How often do you remember to take your medicine more than once a day? So, okay, there's one. Okay, we have one. But the point is, not to say that this will solve everything, but I think getting to a place where we have a once-a-day therapy is a huge step forward. There's additional correctors being developed here by different companies. There's an amplifier I mentioned, which is being developed. And I was going to mention some results that were reported over the last year about an oligonucleotide approach, which is a little bit different than what we've been describing before. And this is with a company called ProQR, and the drug is called QR010 or 010. Take your pick. So this concept here is that this, rather than giving a compound that, like a little molecule, or it is a molecule, but it's a very different type of molecule. It's actually a piece of RNA, and RNA is some of that machinery that helps go from the gene to the protein. It's sort of the intermediate step. And this little RNA sequence is 33 pieces or nucleotides long, and it has been stabilized, and then and they've been doing most of their work with delta F, but they are expanding it to other mutations. So, but I'm going to show you the work with delta F, but the neat thing is it has the potential to be theoretically sort of customized to any CF-causing mutation. But what they've done is this, when it enters cells, it goes to the RNA, which again is the template that comes from the gene, and it helps kind of, sort of anneals or sticks to the RNA and helps it put in restore putting in that F508. So the neat idea is you're actually starting with delta F508 code here, ending up with normal protein there by that change in translation. So that's a really interesting approach that is actually, rather than making delta F508 work better, you're actually fixing delta F508 and putting it back in so it works correctly. So they did a proof of concept study in which they measured CFTR activity in your nose. Think of it as a sweat test on your nose. It's called the nasal potential difference. If anybody's ever had it done, it's very wet, but it doesn't hurt. But I've had it done quite a bit. My nose is a testing ground and training ground for a lot of people through the years. Yeah, I've had more people in my nose than I want to admit. So each of these stars is when we dosed patients with this drug by literally a little squirt up their nose. It was a little spray thing. It was 3 times a week for 4 weeks. Small numbers, 10 patients with 2 copies of F508, 8 patients with 1 copy. All of them were adults. They were stable. They're not unmodulators. And the good news is nobody's nose fell off. That's a good start. So we were very happy to see that. But we measured what was happening with CFTR activity sort of at the midpoint at the end of that study. And I'll show you those results, and just take me a moment to walk you through them. So what we're looking at here is CFTR activity, and the darker kind of orangey color, yellow-orange, is the time that patients were on drug, and then this is the after point, 2 weeks after that they followed, or actually it was about 3 weeks. And what we saw is that the potential difference went down, and that actually this is evidence that CFTR is working. And it dropped by 4 millivolts, and that effect was actually very similar to what was seen with the early ivacaftor studies with G551D. So at least when you put it up your nose, it seems to be able to make CFTR work better. And on the right side, what we're looking at are all the different ways that we can measure, or sort of analyze that NPD data. Like the darker color is the average number. The orange is the most polarized. The next one's the left side. Next one's right side. So the point is, every way you looked at it, it showed the same thing. At the day 15 and day 28, there was improvements. And actually, what was interesting is that those improvements lasted for at least 3 weeks. So suggesting that the drug may not need to be dosed very often to be effective. Down below, we're looking at sodium transport, and this is looking at the treatment period. I didn't talk in great detail, but it turns out CFTR, in addition to being a channel that moves chloride and bicarbonate, it also regulates sodium transport. It sort of helps put the brakes on that transporter and makes sodium movement less, and that's important in maintaining the normal hydration in the airways. And what we saw was that not much at day 15, but actually on day 28, that regulatory activity of CFTR was restored. It was able to improve the sodium transport about 10 points, which is a fairly big effect, actually. And this, again, is looking at it in all the different ways we looked at it before. One nostril, two nostrils, nostril A, nostril B, et cetera, and they all showed the same effect. So providing us some evidence that this approach could, in theory, be effective by giving the drug into the lungs. They are now doing a nebulization or an inhalation type of approach, and that study should be completed by August of this year, so it's going very quickly. Anti-infectives. These are drugs that are trying to treat infections in CF, and obviously there's a lot of intravenous and oral antibiotics available. I'm focusing primarily here on, not completely, but primarily on therapies that are inhaled. Sorry, one second. Okay, and the top are examples of drugs that are available that are target Pseudomonas, as Trianam and tobramycin in a variety of different forms. And there's a number of additional ones which are in clinical trials. There is a inhaled form of vancomycin that goes after staph. There is a inhaled form of, it's a combination of tobramycin and a second drug, which may be a more effective way to go after Pseudomonas. This is a study being led by our colleagues up in Seattle. Shout out to Dr. Hoffman's group and Dr. Goss, who are using it. Woo, woo, woo. In which they've taken a neat idea. They've used this drug that's used for a very different purpose to try, it helps bind up iron, and that, we believe, may be something that allows Pseudomonas to grow and thrive. And by using this drug to sort of capture that iron, it may be a really unique way to go after Pseudomonas, and that study's ongoing right now. And then the last is using inhaled nitric oxide, not nitrous, that's a different story. But nitric oxide is a natural antimicrobial. It's something that is normally made in our bodies all the time. It does a lot of different things, but one of which is it helps kill bacteria. And we use it in very, very, very sick patients to treat pulmonary hypertension in the ICU. But it also can be inhaled and increase your ability to kill a variety of different pathogens. It's not real simple because you have to inhale it over a long period, so there's still some figuring out to go, but we're testing through this study whether it has the capacity to offer treatment to really tough to treat bacteria and other infections. So a lot of stuff going on that front. I'm going to mention, also I'm going to show you a little bit about some of the anti-inflammatories. As I mentioned in CF, there's a problem with too much inflammation, and that is ultimately the thing that damages the airways and leads to the bronchiectasis and all the downstream problems. So theoretically, if we could halt or slow down inflammation, we'd really keep the airways stiff, strong, and capable of working normally. There's a number of different approaches that are being tried here, which are currently in phase 2 studies. And there were some recent results that were reported by a company called Corbus, which I'm just going to show you some of those results in a moment. It's called Anabosum, JBT-101. Just to make it interesting, if I'm not mistaken, this guy is kind of it's a cannabinoid receptor agonist. And so cannabinoids, anybody heard of those around here? Anybody from Seattle heard of that around here? Anyway. It doesn't mean prescribe cannabis. It just means that there are something in cannabis, one of the many, 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 many molecules that may have some anti-inflammatory activities. So this study, which is a little complicated, but I won't get into great details, but about 70 patients were dosed with one of 2 doses that were relatively low versus placebo. And then they were re-randomized into a longer study of a higher dose, 1, 2, and placebo for about 8 more weeks. And so these are the results from those studies. They're not big numbers, but they are very intriguing and certainly provides support for going forward with this approach. So a total of 85 patients were enrolled. Lung function, kind of moderate, what we consider moderate lung disease range of about 63 to 65%. Kind of young adults, 26 to 30. There are no real big changes in adverse events, lung function, or symptoms. Not surprising. It turns out actually anti-inflammatories don't often change those things a whole lot. But this they did show was a really pretty significant reduction in the risk of exacerbations. This was kind of the exacerbation risk in patients who were on placebo, and this has kind of been normalized to a yearly number. This is in people who were on any dose of the anabosem, and this is the patients who were on the highest dose, and they actually had about a 75% reduction in risk of exacerbation, meaning a need for antibiotics for new symptoms. And so, pretty profound effect. On the left side is looking at the effect of the drugs at different doses on one of the sort of mediators of inflammation. It's called IL-8. It's basically a driver of making neutrophils misbehave. And basically what they found is you got certainly to the higher doses, there was evidence that the levels were going down in the sputum of the CF patients. So this will be going, I got 10 minutes, I gotta move. All right, sorry. So moving mucus. There are a lot of approaches that are going on here. These are approaches that are trying to restore water movement by blocking sodium channels. Mannitol, which is approved in Europe, which helps to try to pull water into the airways and loosen mucus. And most recently, a drug that's called Oligo-G, alginate polysaccharide. It basically chops up mucus. And so these are approaches which are either in or coming into clinical trials. I wanted to mention 3 studies that are being that are ongoing and supported by the CF Foundation. One is looking at non-tuberculous mycobacteria, a real problem, and abscessus, which is going on right now in Colorado. The Czech SC, which is basically helping to understand relationships between CFTR modulators and changes in sweat chloride. And then the RARE study, which is really focused on obtaining new cells from patients with rare CF-causing mutations. And I'll briefly mention each of those. What you're looking at here is the results of a number of CFTR modulator studies in which they looked at the change in sweat chloride and the change in lung function. And while it may not be possible on a person-by-person basis to predict exactly how you're going to do by how much your sweat chloride changes, certainly if you look at the groups, you see a clear relationship that the further your sweat chloride goes down, the higher your lung function goes up. So that is giving us some indication that this is a biomarker that we think we'll be able to use to guide therapy for patients, knowing that a short treatment may predict a long-term benefit and may simplify how we do CF clinical trials. Then next, I just wanted to give a shout out for an upcoming study that will be happening here at Stanford. This is understanding patients who have rare CF-causing mutations. As I mentioned before, there are patients who don't have clear support at this point for use of CFTR modulators. And some of these actually really require having cells derived from patients to even look for drugs. I got 1 minute? 18 minutes. Oh, I got 18 minutes. I thought you said 10 minutes. I was like, dang. I was really going slow. Okay, I'm fine. I can slow down again briefly. I got about 18 minutes left, by the way, so we're right on time. So this concept here, though, is that we will get cells from patients who have rare mutations. The first group of patients we'll be looking at are patients who have 2 copies of stop mutations or premature termination codons. And these are the same type of medication that Adalorin was trying to improve function in. And we believe that getting these cells from the patients will allow us to develop the right type of testing platform to actually see these drugs. And so we'll have patients being referred to one of 5 centers across the U.S. And so if you know of people or have an interest in learning more about it, Colleen Dunn is in the back. So she's sneering at me right now. So anyway. Another thing that I wanted to mention that just happened in the last few months is using test tubes or studies in the lab to actually go directly to patients. And as I had mentioned in all those studies before, we sort of selected patients to be in studies based on their mutations, and that's a huge advance. But what about people who have really rare mutations, 5, 10, 20 people in the world? How do you do a clinical trial in those patients? And the concept here is that in certain circumstances, what you learn in the test tube may allow you to bring those drugs to those patients with FDA approval. Why is approval important? Because that gives you a leg to stand on when you fight with insurance companies. And so this was some work that was done by Fred Van Goor out of Vertex, and he expressed 54 different CF mutations that all are sort of like a substitution problem. So they make protein, but they don't work quite correctly for a variety of different reasons. They put them in a common type of cell, and they did a lot of work making it a very standard test. And these are all those mutations lined up. There'll be a test at the end of this to make sure you all got them correct. But the black is sort of the natural activation of CFTR by the normal signal, and the white on top of it is the extra oomph you get by adding ivacaftor. And what you can see, there's a group of patients who clearly seem to show an extra oomph when you add ivacaftor. And based on this type of data, coupled with a little bit of clinical trial results, the FDA expanded the ivacaftor label to include 23 more mutations than it had previously. And that is a huge thing. And there were sort of some caveats, so it's not like you can say, oh, it works in the lab, therefore we don't study in people. Before you can, the situations where that probably can be done is really about label expansion. So it's a drug that's already been studied carefully. We know it's safe and well tolerated. It has, again, a good safety record. And we understand the mechanism of action, how it's helping, what its target is. So there are definitely, this isn't going to be for, anything you find in a test tube gets to jump straight to therapy. But the point is there's a path now for some of these that's really new and hadn't really ever been taken by the FDA before. So we're very excited about that. So last little bit, about, I'm going to say 14 minutes, we'll talk about clinical trials in a test tube, which is sort of jumps off from that idea. And this, again, is for testing CFTR function in patients who have rare mutations in cells. Examples are patients who have premature stop or termination codons, splice mutations, and a variety of others. And we can do this, there's sort of two things we can do. One, we can look at patients who have really rare mutations, or perhaps, let's say we get to a world where we got 5 different therapy choices. What's the right choice for you? What's going to give you the best long-term benefit? And we hope that we can use these types of testing systems that come from patients to figure out the right drugs for patients. So this concept is called, some people call it theratyping. Rather than sort of putting everybody into these buckets and saying we target the drug based on this, we take a unknown or poorly described mutation and we test drugs and determine whether it actually shows some benefit in a laboratory environment. And theoretically, then we can turn around and test it in a patient. Patient-derived model systems are basically cells that come from patients, and they can come from different places. GI tract is the furthest along, and this is what organoids and enteroids are, where basically little snippets of rectal tissue can be grown and be used to study different drugs and CFTR activity. More recently, there's been work on brushed cells in the lung and the nose, which may be able to also do that in a little easier to get sort of fashion. And ultimately, stem cells are a great option once some of the particulars are figured out, in which you take cells from the blood but coax them into becoming the cell type that you want to study, be it an airway cell or a GI cell or a liver cell or whatever. So the farthest along are the intestinal organoids, and most of this work has been done in the Netherlands by Jeff Beekman and the group in Hubrick. And basically the idea here is you take a rectal biopsy, you isolate the stem cells, and you grow them in a culture. It's called 3D matrigel, and then you stimulate them and they swell when CFTR works because the CFTR transports water. And it's probably a little hard to see here, but here's a control condition at 0, 30, and 60 minutes. And these little green guys are staying about the same size. In this situation where we've added modulators and then stimulated CFTR for 30 and 60 minutes, we see they get bigger. And you can quantify that swelling over here is looking at how much these guys are swelling over time. And this is an example where we have the activation of the CFTR in that organoid from that given patient by the normal way. And this is in the addition of ivacaftor. And we basically made it easier to activate the CFTR and potentially showing us that that drug is active. Here's an example where it's having some effect, but it's less. Here is, again, a known mutation, and here is one that didn't work. And so the point is we can use this model system to sort of test whether adding a modulator improves the function of a given CFTR from a given patient. This has been tried, showing an example that drugs that suppress premature stop mutations, this approach is able to detect that. And what we're looking at is the swelling of some of these cells when stimulated with a known suppressor. This is called G418. It's not a drug we can use, unfortunately. It's toxic over time, but it's basically a relative of gentamicin that's very good at suppressing stop mutations, but unfortunately it can be very hard on cells. But this upswing is showing it can detect it, and interestingly, in this scenario of a patient who had a stop mutation and a second mutation without function, adding VX770 and 809 actually improved it. So showing us that this model system indeed might be able to be adaptable to people with really rare mutations. We're going up the nose, and specifically primary airway cells from the lungs have a great track record of restoring CFTR function. But can we use nose cells, which are actually not that hard to get? We can, beyond the usual way I go to my nose, you can actually take a little scoop and get them and grow them. And there's been some real advancements in how we grow cells that lets us go from a few cells to a lot of cells. And how should we grow them, though? There's a lot of questions. Do we grow them as a sheet of cells? Do we grow them like spheres, like the enteroids? Do they behave like the lung cells, and do they predict clinical response? And there's a number of studies that are sort of ongoing trying to figure this out to determine how good a nose cell can inform us about CFTR therapies. And one example here, this is just looking at airway cells grown in 3 different medias. These are nose cells that were brushed and expanded and grown as a sheet. And this is one type of media. This is a second type of media that was used for most of the new Vertex drugs. This is one that's available that you can purchase. And the point is they can look a lot different. So we got to figure out what's the right type of media for it to be the most predictive. But they can definitely, this is a sheet of cells looking down at them, they make the right cells, they have sort of the right configuration, and they definitely can detect CFTR activity. And what I'm having you do here is look right kind of in this area. We're looking at activation of CFTR from a sheet of nose cells. And this is from a patient with 2 copies of F508. And this is a little bit of activation at baseline. This is better in the presence of 809 and stimulated with 770 and similar with 661, which is tezacaftor. So certainly giving us ideas that this could be an option. Now I really have 10 minutes. Another approach is to grow the cells as nasal spheres. We like this concept because it's faster and it doesn't take so long. It takes about 2 months to get cells into a sheet. But we can grow them in a way that's not that different from those organoids. And in the baseline, we have cells here where we've stimulated them, CFTR works, and they swell. And they really have a cool picture. It looks kind of like a, well, I don't know, it's just a cool picture. But this is a ball of nasal cells that represents a sphere, which has a number of the different things we like to see that tell us that indeed they're behaving like airway cells. And so what I'm showing here is that when we grow cells as a monolayer, or a sphere, they actually line up pretty good. And what this is, I know it's a little hard to see, but we basically brushed nasal cells from CF patients and non-CF patients. We grew them both ways, sort of side by side, sphere here and monolayer here. Same person, but different ways. And then we looked at how well their CFTR works in the monolayer and how well their CFTR works in the sphere. And the point is they work really quite similarly. They line up about this R squared, which is a way of looking at how well they line up, is quite good. It's about a 0.7, and we're really pleased to see that. Down below here is looking at a variety of different patients, looking at how well correction or modulation lines up. Again, each dot is a person, and in the up and down direction is the change with the X809 in the monolayer way of growing them. And on the x-axis is the change in CFTR activity in the sphere way. And again, they line up really nicely. This time they got a 0.81, which 1 is perfect. Nobody's 1. So the point is we felt like this might be a nice avenue that is faster and perhaps a little bit easier. And so we're ongoing doing this type of work still. And finally, just to mention, people respond differently to the same therapy. And this is just highlighted in this slide. What we're looking at is a phase 2 results from an early study of lumacaftor, ivacaftor in patients with 2 copies of F508. And each line is a person and how much their lung function changed in response to either being on active drug, which is these kind of bigger purple ones, or the red guys are the patients who were on placebo, and that's kind of shown here. And what you can see is that overall, the patients, there are patients kind of down here who do not seem to show much, if any, benefit. Their lung function on that seems to go down while on drug. While there's a larger group, but not all of them, that tend to go up, which is shown over here. What's different about those patients? Why do these guys respond and why do these guys not respond? And so we hope that using these kind of model systems, we can better understand who responds well to a given drug, perhaps differently than how we do it now, where we just say, let's see how you do and see me in a month or 2 months and how do you feel? And that's good, but I think we might be able to do better. And so that's really where we hope these types of model systems will become more valuable in helping to find the right modulator, right therapy for a given patient. So we're almost there, coming around. We have this concept that we can take cells from patients, study them in a way that is reproducible and allows us to test different types of conditions and perhaps use that model system to predict what's the right choice for a given patient for therapy, be it a rare mutation or be it a lot of options for a more common mutation. So I hope I can send the message that CF therapies are breaking a lot of new ground, and things are moving extremely fast. I mean, some of these slides I used, I had the audacity to use 2 years ago, and they're already out of date. And so the good news is I'm going to have to update my talk next time I do this. We clearly know CFTR is makes great sense to fix. I mean, that sounds obvious, but we didn't know that until that happened with ivacaftor and subsequently all these other drugs. And so we are getting more and more modulator penetration into patients, and we're extremely excited with where that's going. The pipeline is full. It's not just CFTR. There are needs today for anti-infectives, anti-inflammatories, mucolytics, hydrators, and all of those are happening and moving forward. And novel strategies are in process that help connect patients to modulators, ensure that all patients ultimately who can benefit will be able to. So I thank you all for your attention, particularly the time man who's keeping me more or less on track. I'm happy to answer any questions. I'll be here all day, but I have to fly out tomorrow about noon. So thanks again. I appreciate your attention. And thanks, Luke, for the...
Thanks, Dr. Clancy. We do have time for some questions. I do want to remind you, due to time constraints, we ask that you limit your questions to one per person. Please speak clearly into the microphone in the room, and remember, a volunteer will adjust the mic and clean it for you between use.
Hi, thanks for your talk. It was great. One question I had, for people with MRSA or pan-resistant bacteria, what new drugs are coming that can help them? Because it'd be great if they could also come to the conference and everything. Hint, hint, wink, wink.
So the question, yes, again, about what type of new antibiotics are under development for pan-resistant organisms, including MRSA and other ones. It's a great question. You know, in the MRSA field, probably the things that are moving the most rapidly would be the inhaled vancomycin products, which are being studied. A company named Savara is in the process of bringing that out. I believe it's a dry powder formulation. Whether it's going to eradicate, it's hard to know. I mean, perhaps it could be an eradication strategy like Toby for early infection. It's a little hard to know for established infection. But that is beginning phase, kind of late phase 2 studies. I mean, literally, we're in the midst of startup right now. So that's getting going right now. That one thing I mentioned about nitric oxide, that in theory can be applied to a whole host of different bacteria. It's a natural antimicrobial that your body uses, but they put it into a concentration that you use where it's much more effective, and it crosses a lot of different types of bacteria. So we're hopeful for some of those really difficult, what are called gram negatives, like even Cepacia or theoretically Stenotrophomonas, Achromobacter, some of these things that sort of have a lot of resistance. These may be options. And I imagine Luke, Dr. Hoffman could give you a lot more than me. That means he's like, okay, no, he's the antimicrobial guru around here. So, but there is definitely action going on in that field.
Wow. One question.
Yes, sir.
Particular small molecule you were working on worked better when the patient only had one copy of Delta 508?
Isn't that amazing?
Yeah, why? I mean, what's your speculation on that?
This is what we call hand waving? No. I don't know, to tell you the truth. I think a little bit, there's a couple things to remember. So the people who had 2 copies of F508, they were already receiving baseline Orkambi, which maybe gives you 3 or 4%. It was a slightly different version. It was tezacaftor and ivacaftor. So they were starting from a different bar, and so maybe they've already had a bump of 3, 4, 5%, and then they had the improvement on top of that. That's what I'm guessing, but it's pretty remarkable. And I think it may tell us that it's not what they call a linear relationship. Once you get enough F508 out, maybe we're going to be in a place where 1 or 2 doesn't matter, which is, I don't think anybody expected that, to tell you the truth. So again, I don't want to, my caution is it's small numbers and things may kind of come out to be a little less, but obviously you see it in 3 drugs had very similar effects, and it was hard to distinguish a big difference between 1 or 2 copies of F508. So we're all fascinated and thrilled by what we saw.
Hello, and thank you very much for this very informative presentation and the wonderful work and research you're doing to help the CF community. I wonder if you have anything to say about perhaps the way that the patients might perceive their environment and their experience and the impact that that might have at the cellular level. Dr. Bruce Lipton has done some work around that and some research, and I don't know if you've been looking into any of that or what your take might be on that.
So happy to try to answer that. So I think, and please, if I don't answer it correctly, feel free to re-ask it. So I will say that when and I think all of us who've had patients go on to highly effective modulator therapies, we can measure different things that do better, lung function, cough symptoms, weight, somewhat a quality of life measure, but very often you just hear, I feel better, and it's rather hard for them to put into words what it is that feels better. And I think it reminds us that CFTR is what we call a systemic disease. It's a problem with a problem that ultimately affects, maybe directly or indirectly, every cell in your body. And helping that CFTR work better helps, I believe, all those cells work more normally, and it sort of improves things that we haven't really thought about how to look at. But it's clearly changing how cells, the metabolism, how they work, how cells behave at a very fundamental level. And it's kind of amazing. I've heard it, Preston Campbell, the big tall guy at the foundation who's got the smooth kind of voice, and he calls it the CFTR light bulb. All of a sudden you turn on the light bulb, and now we are seeing what the difference is. And the normal, on average, a CF patient needs 50 to 100% more calories than the average patient. Some of that is because they don't absorb, but a lot of it is because they burn energy differently, and that's a very fundamental cell question. So it's a long way of saying I don't quite know why, but I think there's a lot of interest in better understanding what is fixed in cells that really translates into patients just feeling better.
Thank you.
Mm-hmm.
Wow. I'm one of those veteran mothers. I have a 27-and-a-half-year-old daughter with CF. And the improvements and all the new therapies is just, we had many years when we were just waiting, and all of a sudden it's boom, it just exploded. The question I have is for patients with the double delta F508, the Orkambi doesn't seem to be working.
Yeah.
Do you think the triple drug therapy would work?
Yeah, great question. So, as I kind of alluded to at the end, even in the best case scenario, there are patients who do and don't respond well. I mean, if I've got heartburn, I do better with, Prilosec versus Nexium, who knows, I don't know. So there's these little nuances we don't understand very well. My suspicion is, there's a lot of reasons why Orkambi may not work really well in F508 homozygotes patients. Again, it has some off-target effects of chest tightness that patients don't sometimes tolerate very well. And again, the effect is just, on average is there, but on an individual level can be missing. And so I'm really hopeful that the switch from Lumacaftor to Tezacaftor sort of takes away some of those off-target side effects. I think that most of the studies of Tezacaftor have not seen that. It hasn't been published yet, but at least what's been presented looks really reassuring. So people who just don't tolerate it all of a sudden may have that opportunity. And then, again, adding the next gen, I think maybe a given person has a more effective step one checkpoint than another, and therefore that Orkambi doesn't quite get the job done, but you add that next gen, it all of a sudden makes a huge difference for them. So I know that's kind of like going another one of these things called hand waving, but I suspect a lot of patients who hadn't responded well will see benefits by adding the next gen, but I can't wait to see.
For all these next generation correctors and modifiers and potentiators, how will they decide which one to bring to phase 3 clinical trial and bring into the market? And when they do that, will they incorporate things like better GI or relieving of GI symptoms or less hemoptysis and that sort of thing? Because all the data you showed focused mostly on FEV1, but CF affects so much more.
Yeah, no, of course. And again, I show that because that's the kind of the easiest thing for people to kind of wrap their heads around. It's interesting too for some of these. I didn't show it, but the improvement in the CF quality of life scale, which again is kind of an accepted instrument or questionnaire basically we use about respiratory symptoms and other symptoms that showed an 18-point improvement with one of these drugs and 20 points with the other, which is unheard of. So really speaking to patients feeling a lot better. So one, it's a combination of things, obviously. If there are toxicities that emerge, meaning people have, stomach upset, they get side effects, they have, for example, like the chest tightness question, if they have other sort of side effects that sort of make it not a good long-term, rest of your life therapy, those probably would sort of put them on the back burner as your first choice to go to phase 3. But the major things I would think is just the clearest sign of activity across a number of different ways to measure it, plus the least side effects and what they call the biggest therapeutic window. In other words, it gives you the most flexibility in dosing. Right now, ivacaftor is performed great. I mean, we really haven't seen many side effects out of it. We've watched for cataracts, but really hasn't popped up yet, and so forth. So people starting to feel better and better about that drug. Triple combo, though, is that's a lot. I mean, that's 3 things theoretically for indefinitely, and so really understanding those safety profiles and interactions is going to be critical for the long-term choice. The good news is we have many choices, and so hopefully one of them will shake out as the best.
Thank you for your wonderful talk. So my question is, many of us have children, and there's other adults here who have transplants. So their lungs have very different cells.
Yeah.
So what do you think about using some of these drugs on transplant patients? Could that be damaging to their new lungs because there's a whole different cell thing that's going on?
Yeah, it's a great question. We don't have a lot of data on that yet. I will say that there are patients who've had lung transplants who are on modulators for the other systemic benefits. I can't speak to experience personally just because we don't have our transplants that we do at Cincinnati Children's are much more focused on young kids, and so we actually thankfully don't have CF patients very often in that scenario. But there definitely are patients out there who are receiving them for other symptom reasons. It's a little tricky because the transplant meds obviously are very, they can have drug-drug interactions, and so monitoring sort of drug activity and levels becomes, I think, a little problematic with some of these drugs. And so hopefully the newer versions that are sort of emerging now would allow us to do this in a way that we feel like we're not putting the transplanted organ at any risk. Again, it's a great question. I wish I could give you more than that, but it's out there being used, but not routinely. I'll put it that way. But it's where we want to go, no question. Oh, and by the way, there is actually a work group that's been established that's really focused on transplant outcomes for CF, and I can give you more information about that, but really it's been an area of interest that is really solidified into a number of centers working together on some of the questions specific to CF and lung transplants. So I can give you that if you'd like that.
My question is about if you're towards end-stage CF and you've suffered a lot of internal damage and everything, these potentiators could really help stabilize you, but is there any new drug coming out that could help reverse internal scarring and all the damage that's already been done?
Yeah, that's a great question. So can we reverse scarring in CF? I think that's another one of those holy grails. I mean, I think we're most hopeful, obviously, with where we are right now, that we can with newborn screening, we feel like in many ways we're ahead of the game in some aspects of CF, and getting modulators started early may prevent things. How about those who've already suffered some of the consequences, and can some of those things reverse? I think some things can. There's certainly evidence that, for example, ivacaftor, if you look at CT scans of some patients, they've actually shown improvement in bronchiectasis. It's probably a relative thing. In other words, a certain level probably can't be reversed, but perhaps a milder level can. I think we're all very curious, can some of the fibrosis that is seen in the liver reverse? Historically, we think of, Fibrosis is kind of an end-stage thing, but I think it's also being realized maybe that's not quite as simple a way of looking at it. There's some drugs that are now becoming available for idiopathic pulmonary fibrosis that really tackle the fibrosis part, the scar. And I could see a place where down the road, as we become more familiar with those drugs, they may actually have a role for CF. And they may not be specific just to lungs. It may actually be that antifibrotic effect may include other places, such as the liver. Obviously, we'd love to see the pancreas restored. That may be a harder row to hoe, if you know what I mean. But that being said, some of the activity may be restored. There's certainly evidence that potentiators can make your pancreas make better bicarbonate release, which probably makes enzymes work a lot better. So there are aspects that we probably still can improve.
Sorry, I came late, so I have a little basic question.
Sure.
What does CFTR stand for?
Yes, okay, that's the name of the gene in the protein. It's a cystic fibrosis transmembrane conductance regulator, a mouthful. And it's whoever, I think it was Jack Reardon, am I right? Paul, are you nodding? Did Reardon name it? Did Jack Reardon name it? So he was very wise to give it this name because of its... That's awesome.
My other question is, sorry.
Got it. So the guys who actually found the gene, yeah. But they named it because of the class of that traffic ATPase family it's in, and that was kind of an appropriate name for it there.
My son is taking Orkambi.
Yeah.
I had gone to a conference in Arizona, and just like some things, I get part of the information, but not all of it. Is there a second Orkambi?
There is. It's not currently available, but it's getting close. So Orkambi is the combination of ivacaftor and lumacaftor, which is basically 770 and 809, which when it's used in the lab. The sort of next version, I guess you would say, of Orkambi, it's called tezacaftor and ivacaftor. So and that's what 661 is that tezacaftor. It's a similar, without getting into the details of the molecule, it's very similar in many ways, but it doesn't seem to have some of the off-target effects, and it may have less interaction with other medicines. So that has been studied into phase 3, and my understanding is that's the goal of including that with next generation correctors, because it's maybe a cleaner way to, it has less likely interactions between the 3 parts of the triple combo therapy.
And the side effects for the Orkambi, is it chest tightness, and what else is the prevalent?
Yeah, that's one that maybe 15% of patients report, and often with time they often can overcome that, but it's definitely can be enough for some patients not to want to take it. It also can have effects on liver function tests, so that's why we have to monitor it at least quarterly for the first year and then yearly after that. But some of the patients who are on lumacaftor did have some increases in liver function tests. The good news is they've always typically come down once the medicine is interrupted. You can often restart it. After that, the other side effects are relatively small and obviously kind of patient specific. I have one patient who is convinced he has diarrhea with it. I'm not quite sure if I believe him, but he does, so it doesn't matter. So anyway, I'm hopeful that when we have the next version, he'll be willing to retry it.
See, my son is just turning 30, and so he goes to his appointments by himself,
Yeah.
and he doesn't want to tell mom everything that goes on. So when I ask him, how's your appointment, he's like, oh, doing great. So I don't get all these details, so because all these HIPAA things, right? So
Right.
mom's a pain in the neck.
Yeah,
but
that's the
all
law.
right.
Sorry.
Thank you.
One last question.
Sure.
Sorry, I did come late, and I know you're trying to keep on track. Can you talk about fast tracking?
Fast tracking, so drugs getting fast tracked.
I mean,
the FDA's.
going into phase 3 with the next gen, and then,
I don't know if I can speak to great detail to the regulatory. Much of modulator development has been fast tracked. And they've been able to rely on a single phase 3 study for some of the drugs to be
And do you think that might happen again?
Hard to know. Since it's going into larger, definitely with the ivacaftor, it was more straightforward because it was a really difficult study population because of the small numbers of G551D patients. My suspicion is that they will do 2 big studies at the same time.
Right,
That's
I
what
mean,
it
you
is.
have 85-90% of people
Yep,
who can
and
take part in this study.
That's my suspicion, but I have not heard their phase 3 programs yet.
Thank you.
Mhm.